Hi friends, hope you have gone through the previous videos in machine learning. So in this video I am going to explain about regularization. So as we are in the third unit, this regularization, it also comes under this third unit under classification and the temporal models. This is the actual syllabus here, and here we have seen the artificial neural networks. We have seen what is ensemble learning. In ensemble learning, we have also seen the bagging, boosting, and all those things. And now we are moving to the next topic, that is regularization. So, what is regularization? Why we need this regularization? That we are going to see in the first. So, while we train the machine learning models, so there may be a possibility for getting this model overfitted or underfitted. Overfitted in the sense almost all the data patterns have been connected through the curve, or underfitted is very long residuals that may be possible. So there may be a chance for any of these situations, that is overfitted or underfitted situation. To avoid these two, overfitting and underfitting of the data set, we are going for this regularization. So the regularization in machine learning, it is used to properly fit a model onto our test set. So what it does is it helps to reduce the chance of overfitting and help us to get an optimal model. So that is the major reason for using this regularization. Before getting into the regularization, let us see what is overfitting and what is underfitting. So first is overfitting. So when we allow a machine learning model to look into the data available in the data set for many times again and again, so this model will find a lot of patterns in the data, which includes the unnecessary data also, because it is repeatedly going on performing the model. So what happens is it finds a lot of patterns which may include the unnecessary data too. So what happens, it will learn, it will really well do this learning process very well on the data set. Also it will fit very well to it. It will learn the important patterns, but what happens is there may be a chance for learning from the noise also. So there will be noise in the data. Because of this repeated learning, there may be a chance for learning the noise also. So what is this overfitting is the scenario where the machine learning model tries to learn from the details along with the noise in the data. So it is going to learn from the detail, that it will do well, but there is a chance for learning from the noise in the data. So and what it does is it tries to fit each data point on the curve. This scenario, we call this as overfitting. So the example curve is like this. Here almost all the data are being connected through the curve. So this scenario, we called it as overfitting. So next we can move to underfitting. What is this underfitting? Is just the opposite of overfitting, where the model has not been allowed to look at the data for sufficient number of time. So in overfitting, we are looking into the data for many times. Here it is not allowed to look at the data sufficient number of times. So what happens is it won't be able to find the patterns that are available in the data set. So it will not fit properly to the data set and fail to perform on new data too. So it is not able to perform well with the fixing the new data. So how we could explain this underfitting scenario is the scenario where the machine learning model can neither learn the relationship between the variables in the testing data nor predict or classify a new data point. So it is first thing, it is not able to learn the relationship between the variables, and the second thing, it is not able to predict or classify the new data point which is being put into the data set. So this scenario we call it as underfitting. So you could see in this particular curve, so the line which defines this slope, the slope, it is not matching with most of the points. The residual length between the point and the slope is high for many of the points. So this scenario we call it as underfitting. Hope this overfitting and underfitting is clear to you. So next we are moving to the other two important parameters which we need to know before getting deep into this regularization concept. Those are bias and variance. So first we are going to look into the bias. This bias occurs when an algorithm or the model has limited flexibility to learn from the data. So when such models or such algorithms, it pays very little attention to the training data, and it just simplifies, or we can say it as oversimplify the data or the model. So therefore what happens is there may be a chance for this validation error or prediction error and training error, all these may occur. So this is the bias condition. So when there is high bias, it causes the underfitting in the model, because as this it becomes oversimplifying, it will cause number of errors, so you are not able to classify the data. So there may be chance for underfitting. Next we could look into the variance. So variance, it defines the algorithm's sensitivity to specific sets of data. So it is just the opposite of what we seen in bias. So the model with high variance, what it does is it pays a lot of attention to the training data and does not generalize. So what happens is there will be a far apart range for this validation error or the prediction error. So this may cause the overfitting. So as it is going to pay a lot of attention to the training data, so it is going to learn again and again more depth into the model, so it may be causing the overfitting. So the bias will be causing underfitting and the variance will be causing the overfitting. So to avoid this problem with this bias and variance, what we could do is we could have a bias variance trade-off there. What is this is an optimal model. To create an optimal model, it should be sensitive to the pattern in our model. At the same time, it can generalize the new data. So to make our model in such a way, we are going to add the Bayes variance trade-off. So when this happens is the bias and the variance both are optimal. If both the things are optimal, then automatically what happens is the model will be sensitive to the pattern. At the same time, it will generalize the new data. So this particular situation we call it as bias variance trade-off. So this is an example which shows the various terms related to the variance and bias. So if there is low bias and there is low variance, all the data will be kept in a single term, so that what happens is the searching of the model or the fitting of the model is not properly done, so it causes the underfitting. The same time, if the bias becomes high and the variance becomes high, it becomes more generalized, and it will be concentrating or pays more attention towards the data, so that it may cause the overfitting effect. So to have a good model, it should have high bias and low variance, otherwise it should have low bias and high variance. If you are able to have this, then the model will perform well, and this situation we call it as bias variance trade-off. And coming back to this regularization, as we have already seen, it is the technique that is used to calibrate the machine learning models to minimize the adjusted loss function and prevent it from overfitting or underfitting. So this is the major objective of this regularization. So using regularization, what we can do is we can fit the machine learning model appropriately on the given test, and we can reduce the errors that can occur in the model. So next we are going to see various techniques which are used in the regularization. So there are two different techniques. Let us see. So the first technique of regularization is ridge regularization, or we can call it as ridge regression. This modifies the overfitted or underfitted models by adding the penalty. So both technique which we are going to see here, it will be adding the penalty, but the calculation behind this penalty will be changing in both the techniques. So in this ridge regularization or ridge regression, how we are calculating the penalty is sum of the squares of the magnitude of coefficients. So you are going to sum all the squares of the magnitude of the coefficients. So you are going to find the magnitude of the coefficients, you are going to square it, and you are going to sum all those things. That will be the penalty equivalent, which you will be adding in the mathematical function to get the model more efficient, avoiding overfitting or underfitting. The next technique is lasso regularization, or we call it as lasso regression. This also does the same thing, that is, it also modifies the overfitted or underfitted models by adding the penalty. Here, how we are going to add the penalty is just the sum of the absolute values of the coefficients. We are not going to make the squares and all those things, just you are going to make the sum of the absolute values of the coefficients. So these are the two different techniques which we are going to see one by one with some example. So first is ridge regularization or ridge regression. As we seen, it modifies the overfit or underfit models by adding the penalty. So how we are calculating the penalty is the sum of the squares of the magnitude of coefficients. So there will be a mathematical function representing our machine learning model which minimize the coefficients and calculate. So the magnitude of coefficients is squared and then added. This is what happening here. So this is the cost function. Okay. So the cost function in case of this ridge regularization or ridge regression is loss plus lambda into the sum of the magnitude of the coefficients of the data. So loss, it is the sum of the squared residuals. Lambda is the penalty for the errors, and W represents the slope of the curve or the line. So this is the cost function with which you are going to find the best fit for the model. So in the cost function, there is the penalty term which is represented using the symbol lambda. So by changing the value of the penalty function, we are controlling the penalty term. This is how we are going to control the model. So this, when the penalty is higher, it reduces the magnitude of coefficients. So let us see with the example. In the curve, there are 2 points, and if we are performing the linear regression in this particular points, if we use the linear regression model, in the linear regression model, the slope passes through both the points, so automatically the loss is equal to 0. Here the loss is the residuals. Here the residual is 0, so loss is equal to 0. And the penalty function here is 1, and the magnitude here is 1.4. So the cost function here is 0 plus 1 into 1.4 the whole square, which will be 1.96. So using this linear regression line, you will be getting the slope which is 1.96, that is the cost function. For the same example, if we are going for ridge regression, the loss is equal to 0.3 the whole square plus the 0.2 square, which is 0.13. So as the line will not be passing through all the points, so there may be loss, and here the loss is 0.3 square plus 0.2 square, which is 0.13, and the value for lambda is 1, and W is 0.7. So now while calculating the cost function, it's 0.13 plus 1 into 0.7 the whole square, which will be 0.62. So automatically comparing these two methods, what happens is the ridge regression will be giving the better plotting. Next we can move to the next type of regularization, that is lasso regularization. So it is also similar to this ridge regularization, which is going to avoid or modify the overfitted models or the underfitted models by adding the penalty. But here the calculation of penalty is by the sum of absolute values of coefficients. So it performs coefficient minimization, but instead of squaring the magnitude, here you are going to take the true values of coefficients. So here the cost function will be loss plus lambda into sigma W. So here, as the same way, loss is the sum of the squared residuals, lambda is the penalty for the errors, and W will be the slope of the curve or line. Similar to the ridge regularization, we are going to calculate the same for the lasso regularization. So the linear regression point of view, that will be giving the same value. So here instead of square, you will be going for same magnitude. So 0 plus 1 into 1.4 is equal to 1.4. When coming to this lasso regularization, here the same way as we did in the ridge regularization, the loss will be 0.3 square plus 0.2 square, which will be 0.13, and the lambda value is 1, and the value for the slope is 0.7, which is same as the previous. Only the cost function will be changing. The cost function will be 0.3 plus 1 into 0.7, which is 0.83. So here also, when comparing the linear regression and the lasso regression will be providing the better plot. So this regularization concept is used to avoid overfitting or underfitting and create a best fit for the machine learning models. Thank you.